Hello, welcome back to our second lesson in physics. This is our Unit C for Science 30, and this is the second lesson in Chapter 1, and last lesson was on fields and field lines, and now we're going to look at equations that we can use to describe these fields. So by the end of this lesson, you should be able to describe gravitational and electric field strength at a given distance from a mass or a point charge using these equations. So that's what we're going to be learning at how to use those equations in this lesson. You'll notice there is no equation for magnetic field strength, so we do not need to know an equation for magnetic fields. All right, now, again, just like in all the other units, we have some formulas in our data booklet that can really help us out as we're going through this section. So these equations are in your data booklet on page 2. And we're going to start by looking at the formula for gravitational field strength. So this is our formula for gravitational field strength. In your data booklet, you'll see 3 formulas that we're going to be using. And here are all the variables that we are going to use with these formulas. The units are also given in the brackets after the description of the different variables. All right, this video is a great video. It actually covers very similar to what we're doing, so another great resource for you to have a watch. So let's take this gravitational field strength formula. So our magnitude of our gravitational field strength is little g. So this is representing the magnitude of our gravitational field strength. How big is that gravitational field? Okay, it is measured in units that are newtons per kilogram. So force per unit of mass. Okay, so it depends on the mass how strong this gravitational field strength will feel on each mass. R down here is the radius, you can't see this, from this or center to center. So if you have 2 masses and you're trying to look at the gravitational field strength, you're looking at the distance between their centers. Okay. A lot of the times we're going to be looking at an object on the surface of, say, Earth or a different planet. So that distance would be the radius of that planet. All right. So yeah, it's the distance from center to center if you're dealing with 2 different like planets or something like that. But if you're just dealing with one planet with something on its surface, it's the radius of that planet. M is our mass of the source of our gravitational field. So if we're talking about the gravitational field on Earth, this might be Earth's mass, and that is given in kilograms. This is also found in our data booklet. You'll see on that same page. Was it back here? No, it wasn't. On that same page, you'll have the mass of Earth given and a few other planets. Big G here, this is a constant. This is a gravitational constant that has been originally proposed by Sir Isaac Newton, but was found by actually calculated by Henry Cavendish way back when. But anyway, so it's a standard. It does not change, and that number is also in your data booklet, so you know where to find it. All right, so what happens if the gravitational field strength if mass increases? So this is our gravitational field strength, little g. What happens if this mass number gets bigger? Right? If everything else stays the same. Well, g is a constant, so we can ignore it. Everything else is staying the same, so we can ignore this. So if mass gets bigger, it's on the top of our fraction here. If mass gets bigger, then our gravitational field strength is also going to get bigger. What happens to the gravitational field strength if the radius decreases or the objects get closer? So that means R gets smaller. If that gets smaller, then the number down here is going to get smaller. Remember, it's r squared, which is going to make this whole number on top divided by a smaller number. So that's going to make this gravitational field get bigger. All right, we're going to look at this. Oh, sorry, what happens to the gravitational field strength if the radius increases? Oh, I did it backwards. I did it as though it decreased. But basically, it's an inverse relationship. So if the radius or distance increases, then the field strength decreases. If the radius decreases, like I did, then the field strength would increase. So we're going to actually do this in a calculation so that you can see what's happening. It's a little bit easier sometimes. We also are going to take a look at a graph here of the gravitational field strength of versus the distance from the center of Venus. All right, so we're looking at the gravitational field strength of Venus and the distance depending on where you are from the center of Venus. So if you can see here, you're not too far. This is as close as you can get measurement wise to the center of Venus. And you can see the gravitational field strength is quite high. It's up near 9. As we get farther and farther from the center of Venus, so like here, you can see that the gravitational field strength has been reduced by quite a bit. Right, so not as strong. And the farther we move farther away from the center of Venus and measure our gravitational field strength, and it's even less. Okay, so the farther we move from the distance of that object, from the center of that object, the less strong the gravitational field is. So just think of that as we move farther from Earth, go out into outer space, Earth's gravitational field is going to have a much and much less effect on us. Okay, and it's called an exponential decrease. You can see it's not a straight line; it's a curve here, and that is because our distance r is squared, so it's making extra exponential difference as we move away. It's going to make a dramatic difference. All right, so let's look at some of the math behind here too. So you have to be able to determine Science 30 how the mass and radius affects the gravitational field. So if they say, if you get a question where it says your distance between the two objects has tripled, you need to know how that affects the gravitational field. All right. Now you need to also know a few things. G never changes. It's a constant, so we can kind of ignore it when we're dealing with everything. What happens if the mass increases? We talked about this. If mass increases, G will increase. So if one increases, the other one is going to increase. Okay. What happens if your radius or your distance between the objects increase? Well, because it's on the denominator. Okay, radius is down here, or distance is down here, the denominator. It's going to cause the gravitational field to decrease. So if R increases, then G decreases. It's an inverse relationship. Inverse. All right, so we're going to do some number subbing here to actually figure out how the gravitational field changes, and this might help you visualize this a little bit easier. So if our original gravitational field strength, which out in newtons, the units are newtons per kilogram, is 2. So this is our original gravitational field strength. And we're saying the mass is tripled. Okay, so if we go back and we think about it, what happens when mass increases? What should happen to our gravitational field strength? If mass increases, then our G should increase as well. They both should increase. So let's see if this works out mathematically. Okay, so it should increase. So to find the actual change, we're going to do some subbing in. So we're going to write the original formula here. And we're going to put in 1 for the constant G, just to help us figure out how this is going to change, by what factor. And we're going to put a 1 in for the radius, because it doesn't change either. So we've got a 1 in for the radius. And the only thing we're going to change is we're going to triple the mass. We don't know what it really was originally, but we're just going to put a 3 in now for that mass to triple it. So 1 times 3 divided by 1 squared, 1 times 1, is just going to be 3. So 3, factor of 3 is what we need to multiply our original gravitational field strength by, or 2 here. So we know our gravitational field strength is going to increase by a factor of 3 now. So we can go 3 times the original 2 to give us 6 newtons per kilogram. All right. So since the only change in mass, it was only a change in mass, it's tripled. We put a 3 in for everything, write 1 for all the other variables, and solve. The new G, the new gravitational field strength, is 3 times the original. All right, so let's try this. What happens if our mass is reduced by a third or down to a third? Okay, so the mass of the object decreases, then we know that G will also decrease. Okay, so that's one thing we should keep in our mind to make sure our math is right. It has to decrease. Since the only change is mass, we reduce the mass to 1/3, right? We're going to keep our constant at 1, our radius at 1, and our mass is now 1/3. Do the math. 1 times 1/3 divided by 1 squared is just going to give us 1/3. So our answer is 1/3 times the original gravitational field strength. So 1/3 times 2 is equal to 2/3. So it has reduced. You don't have a full amount anymore. Okay, so the new gravitational field is only 1/3 the times as big as the original field, because our masses have gotten smaller. All right, so what happens if we do this for radius now? We're going to take the radius, or the distance between the two objects' centers, and we're going to double it. Right? Well, we know before, if we increase our radius, our actual, it's an inverse relationship. We're going to decrease our gravitational field strength. Okay, so we should see a decrease. Well, let's see if this is going to work out. Since the only thing that's changing is our radius and it doubles, we put in a 2 for r. So now we're changing r here. So r goes there. Our mass is staying the same, so we're going to leave it as a 1. Our constant's always the same. Now down below here, don't forget it's r squared. So 2 squared is 4. So we're going to have 1/4 now. So our gravitational field strength is changing by a factor of 1/4. So it's only going to be 1/4 of the original field strength. So 1/4 of the original field strength is 1/2. Okay, so if we increase our radius by 2, our gravitational field strength is decreasing by 1/4 because of that exponent, instead of just decreasing by a half. All right, and lastly, if our radius is reduced to a third, what might that look like? If our radius is reduced, that means the objects are getting closer. All right, and so our gravitational field strength should increase. So let's try it out. We're going to put in 1/3 for r, and everything else is going to be 1. 1/3, so 1/3 squared, so that's 1/3 squared becomes 1/9. Right, as a fraction. And remember, 1 divided by 1/9, you flip the fraction, so you would get 9 times. So if we reduce the radius by 1/3, we actually are going to increase our radius, our gravitational field strength by 9. Okay, so we're going to go 9 times our original gravitational field, which would give us 18. So let's do this again. So if we reduce our radius by 1/3, we are going to increase our gravitational field strength by 9. That's quite a lot. Again, it has to do with the exponent, right? So it's not, all right. Okay, so now when you're also solving some of these gravitational field calculations, you are going to need to do some conversions. So I just have a few conversions on this slide, and these are conversions for the distance, right? So sometimes they'll give the distance in between the two objects in meters, and you have to put it into kilometers, or vice versa. Actually, let's go back and see on our data booklet, what do our units need to be in? Oh, here we go. Yes, our units need to be in meters when we're dealing with the distance between the two object centers. So whenever we're converting, we're needing to get to meters. Yes, so if you want, there is a data booklet table in your data booklet on page 1 that can help you do the conversion. And I've got a simplified way to think about this. If you have this already down pat, then don't use this way. If you know how to convert between meters and kilometers and all that, micrometers, then don't use the way I'm going to show you. If you're always finding this confusing, you can use this data booklet and this method to figure it out. So if you're moving out or away from meters, you divide on this data table. And you can use these numbers here to figure out what you're dividing by. So if you're starting at meters, this is our base unit. So these are the meters. And if you're moving out in either direction, you can divide. All right. If you're moving in from either directions to find meters, then you can multiply by the values that are over here. So let's take an example here. We have 25 meters and we're trying to get to kilometers. So we're at our base units of meters and we're trying to get to kilometers. So we're going from meters to kilometers. So we're going out, we're moving away from the center. So we're going to divide, and we're going to divide by 10 to the 3. So you can see what we've done, 25 divided by 10 to the 3, and that'll give us our kilometers. Say you already have kilometers. We have 500 kilometers and we want to go to meters. So we're at kilometers and we want to go to meters. So we're moving into our base unit. So we're going to multiply by our 10 to the 3. So let's look at this again. Now, this only works if you're dealing with the base unit, right, of meters. So 1400 nanometers. So we're here and we want to go to meters, which is going into the middle. So we're moving in, we're going to be multiplying. And what are we going to multiply by? 10 to the negative 9. 10 to the negative 9. Okay, let's try another one. We've got 42 meters to micrometers. So we're at meters, so we're at this base unit, and we're going to micrometers. Micro is right here. So we're going into micrometers. So we're going to multiply by our micrometers is 10 to the negative 6. Oh, this one's got an error in it. Oh no, it's because I did it wrong. We're going from meters to micrometers. Okay, so we're going out. That's why. So we need to divide. I read it backwards. I thought we were going from micrometers to meters. So we have meters and we're going to micrometers. So we're at the meters and we're going to micrometers. So we're going out or away from the base unit. So we're going to need to divide when we're doing that. And there is our micrometers, 10 to the negative 6. Oh, no, micro. Oh my gosh. No, yeah, micro. Micro is 10 to the negative 6. Yeah, this one's really wrong. That says 10 to the negative 9. Okay. Alrighty. So that's just a quick review. If you are struggling with this, please connect with me and we'll go over some of these. If you already have this down packed, then don't use this method I just showed you. It might mess you up. All right, gravitational field strength example. Let's see. Calculate the value of the gravitational field strength at the Earth's surface. All right. When we have no values given to us in a question, Like there's nothing here other than it tells us stuff, but we have no numbers. That means we're going to have to use some of the data booklet numbers to figure out. So there's a lot of common values that are given to you on page 2 in your data booklet. You can see the mass of Earth there. You can also see the radius of Earth. And if we're talking about Earth's surface, then we can use the mass of Earth. And if we're talking about the surface of Earth, that means we just need to find the distance from the center of Earth to the surface, and that is the same thing as the radius of Earth. Okay. So we can use our formula here that's from our page 1 in our data booklet to find the gravitational field strength at Earth's surface. So we're going to write out our formula. G equals big G, which is our constant, the mass of Earth divided by R squared. And I think I might just go back here just to work this with you. So we're going to write out G, our gravitational field, our constant, our mass of Earth all over R squared. Oh, and G is not on this page here. All right, so we need to find G, and this is on our page 1 with all of our numbers, and G is 6.67 times 10 to the negative 11. So you would write 6.67 times 10 to the negative 11. I'm not going to worry about units at this point. We can leave the units out, but the next page does show you what happens to the units. And then we need to add our mass of Earth, which is up here, which is 5.98 times 10 to the 24 kilograms. Again, I'm just going to leave out the units for now. All over the radius of Earth, or the distance between the two places that we're looking at. So we're looking at the surface of the Earth to the center of the Earth, and the radius is 6.37 times 10 to the 6 meters. And this, don't forget this is probably the biggest thing that people forget, is to square that radius. Now, if you want to pop that all in your calculator using brackets, you go ahead. Some people like to square this number first and then multiply the two top numbers. Remember, if there is no multiplication, adding, subtracting, no sign there, then it's two brackets, you're multiplying. So you're multiplying these two numbers together, and then you're dividing by the square of this number. So this number times itself, or squared. Now, the answer should be this. If you are not getting that on your calculator, I want you to look at the keystrokes on page 330 of your textbook. It actually has the keystrokes there for a graphing calculator and how you would put this calculation right into your calculator. If you are still not getting the right answer, you need to connect with me immediately, because you may be putting in the times and the 10 improperly, and you'll get the wrong answer every time. For the times and 10, you should not be going times 10 on your calculator. You should be using some button like the EE or the EXP button to be doing that in your calculator. If you're trying to use the hat button or that one, you're gonna get things all messed up. So this is a good thing to connect with me on if you're not quite getting this right answer. Your answer should only have 3 significant digits, because your numbers in your variables only had 3 significant digits too. So we need to round that off to 9.83 newtons per kilograms. All right. Now, there is another formula, and this is where you can take that gravitational field strength that you just found, and it allows you to figure out the actual gravitational force that's acting on an actual mass. So you can put a mass, anything, maybe it's U, whatever it might be, you can put a mass in there and you multiply it by the gravitational field strength that you just found, and you'll find the force of gravity on you, or whatever that mass is that you've put on there. So this is slightly different, so don't get the two formulas confused. They're right beside each other in the data booklet. So here's an example based on the gravitational field strength that you just calculated 2 slides ago to predict the force exerted on a 100-kilogram person. So there is our gravitational field strength that we just calculated 2 slides ago, right? And here is our mass for who we're calculating what the force of gravity is for on this person. So we're going to multiply them together, and then this is the force of gravity that that person is going to actually feel. So read through another example on page 331. There's another example of finding the gravitational field strength and then also finding the force exerted on some object that's in that gravitational field. Okay, so 2 separate formulas, but they are connected. All right, electric field strength. Very, very similar formula. It's going to look very similar. You're like, oh yeah, I've seen this before, right? So you got your electric field strength. So instead of G, little g, you have big E. And you've got these lines here. These lines mean absolute value. You've probably come across that at some point in math. 2 big lines and a number inside. Absolute value, it means you always take the positive. So if the answer is negative, you just change it and you only take the positive number. Okay, so to calculate electric field strength, again, this equation is on page 2. You still have a constant. In this case, your constant is represented by little k, and it's called Coulomb's law constant, 8.99 times 10 to the 9. You can find that in your data booklet. You don't have to memorize it. Instead of mass, like you do with gravitational field strength, you're dealing with charge. So we need to know the charge of our source causing the field. All right, so Q here is the charge on the source, all right, and it's measured in coulombs. So that's the unit that we use to measure charge. Okay. Down here, it's again distance. It's measured in meters, and it's the distance between the 2 objects, the center of each object. Again, squared. Don't forget to square. People always forget that. And if your charge, this Q here, is positive, it means the object has lost electrons. So that's the only way you're going to get positive is if you lose electrons. If it's a negative charge on it, then it means it's gained electrons. All right, same deal. It looks really similar, doesn't it? So the electrical field strength and distance. The farther you get away from that source causing the electrical field, the field strength reduces exponentially. Okay, or exponential decrease, I should say. The field strength decreases exponentially. Right. As you get closer, the field strength increases exponentially for the same reasons. So I'm not going to go through that whole table thing again, but it's for the same reasons as the gravitational force. This video is an awesome video too. I suggest watching it after you've watched this video. All right, so here's an example of finding the electrical field strength. What is the electrical field strength? When you are this many meters, so 7.5 times 10 to the negative 1 meters from a 2.8 times 10 to the negative 3 Coulomb charged object. Because there's no sign here, that means that object's charged positively. Right? So a test object, if it was a negative test object, it would go away from it. For our field lines would be drawn away from this object. But anyway, we don't care about the field lines right now. What we care about is the electric field strength. And that's where you're going to pull your formula from your data booklet. Electric field strength is equal to our constant times the charge on the object divided by the distance, how far it is, squared. So you write out your variables. Really good, important piece here. Write out what you know from this formula so that you can figure out what you're trying to find. So we know our radius and we know our charge from our question. And we're trying to find our electric field strength. So we plug in first our constant, which is from the data booklet, 8.99 times 10 to the 9. We plug in our charge, which is from the question, 2.8 times 10 to the negative 3 coulombs. And then we plug in our distance, 7.5 times 10 to the negative 1. And don't forget to square that distance. So square this, multiply the 2 on top together, and divide by the number on the bottom. Make sure you get this answer. Now, we can only have, in this case, our 2 significant digits because our charge, we only got 2 significant digits there, so our answer has to be rounded up to 4.5 times 10 to the positive 7 newtons per coulomb. All right, here is another example of finding the electrical field strength. So another question. Electrons escape from your hair when you comb it, and your comb develops a charge of -4 times 10 to the negative 6 coulombs. Find the electric field strength half a meter from the comb. So write down your variables. You know your charge of your source, the charge on the comb from the question. You know your distance from the source, 0.5 meters. What is your field? So we're going to write out our formula from our data booklet. Pop in our constant. You can pause this video and then go ahead and try this. See if you can put all the variables in the right spot. Pop in the charge coulombs and then pop in your radius and square the radius. Now, this answer gives you an answer that's a negative answer, but remember, electric field strength is always going to be positive because of these absolute value lines. So we take the positive value. And we only have 2 significant digits in both of our numbers that are in our equation, so we can only have 2 significant digits in our answer. Again, though, we can do and take our electric field strength that we just calculated and use it to find the electrical force on an actual object in that electrical field. Okay, so instead of needing to know the mass of the object that's in that field, we need to know the charge of the object that's in that field. So we found the field in our last question. So based on the electrical field strength you calculated for the comb on the previous slide, that's E here, predict the electrical force exerted on it by an electron. So now we're going to take an electron and put that in our equation. And we're at the same distance, which is where we did our electrical field strength. But we don't need that amount there because we've already found our electrical field strength. So we're going to take our electrical field from the last slide, 1.4 times 10 to the 5. That's what we calculated. And then we're going to multiply it by our charge on it, our electron that we've put into this field, -1.6 times 10 to the negative 19. Multiply those together, you get -2.2 times 10 to the negative 14, but we have our force is going to be a positive value here. So this is the force that the electron is going to feel when you put it into this electrical field that we've just around the comb. All right, so make sure that you can do all those calculations on your calculator. If they're not working out for you, make sure you get a hold of me. Just a few more pieces here on grounding wires. We did talk about grounding a little bit when we talked about lightning rods and then having a quick route to the ground to get rid of those electrons. And grounding, that's what it means. It's providing a path for electrons to flow from an object towards the ground so it becomes uncharged, so the object can uncharge itself. Okay, so grounding wires, you saw them with the lightning on the house, but they can also, you've probably seen them on gasoline trucks. They prevent the buildup of negative charges on those trucks. You'll see them hanging down. Without that, the negative charges might jump and create a spark, which might ignite the fumes or the gases that are in that truck, and that would be very dangerous. So we also will see grounding wires here. There's our grounding wire in our plugs that help keep us safe. It's the same kind of idea as having aluminum straw. So if you were drinking hot water out of an aluminum straw, it would get very hot. If you had a plastic straw, you're not going to feel that heat the same way. I wouldn't drink out of that. I'm not quite sure about that. But anyway, it's the idea of you have a conductor as like a handle on a pan, you'll feel that at the end here. Whereas if you have something that doesn't conduct like plastic, you won't feel the electricity here. Okay. There's also a question here, why don't birds get electrocuted? And what would you do if this power line fell on your vehicle? Think about it. So one of the reasons that birds do not get electrocuted is because the electricity wants to take the easiest route, basically, the lowest resistance route. And birds actually have a higher resistance than the wire that they're standing on. So it's a lot easier for the electrons to just continue their path through that wire than to go through the bird and out the other leg of the bird. So the high resistance of the bird prohibits the electrons from bothering to go through there, so the current won't go through the bird. So they takes the least resistant method. Now the question about whether to stay in your car or get out of your car. If you can stay in your car, then you're not going to allow the circuit that, if those wires are alive and they fell on your car, to be completed if you stay in your car. Okay, if you get out of your car and step out, then those electrons are able to get to the ground, because right now they can't get to the ground because your tires are there, right? So they're not getting to the ground because their tires are insulators. But as soon as you step out, then those electrons can go through you from the car to the ground, and that will give you a giant jolt and could kill you. So you need to be very careful if you're going to get out of your car. And in this video on the next page, the only reason you would get out of your car is if it started to catch on fire or smoke or something like that and you had to get out of your car. Then you would jump, keeping your feet together. You just don't want to be touching the car and the ground at the same time so the electrons can get through to the ground. You need to jump, keep yourself tight so they can't jump with you, and keep your feet tight so that you're all landing in one spot. This video does an amazing job of showing this safety piece around that, and actually I was mesmerized by the video. It was good acting. Well, as good as it gets for a safety video. You may have even watched this video and if you took some driver's ed courses, but it's a little intense, but it's pretty valuable video to watch. It'll stick with me for a while. Alrighty, anyway, that's the end. These are some of the resources I used to create this. I had permission from these people. So thank you very much. And if you have any questions, make sure you get a hold of me.